Okay, all right. So welcome back. Last Friday was also a holiday, so again a long break. I have put this assignment on Google Forms. Have you got the email?
Yes, I got it.
Okay, and so I think I've given some time. Maybe by Friday you can do that. I understand that it's not so easy to do if you are drawing pictures. So don't try to draw pictures and all that. That you can do on your rough book. You just need to write, 3, 4 English sentences. How you did it. I just wanted to get a feel of how you will do such a question. Okay, so yeah, so let's start today's class. I'll share the screen. Could you please confirm?
Yes, I can see it.
You can see the screen, but yeah. So, oh, by the way, I saw this email that November 21st exams are starting. You also got this email?
Yeah, I got the timetable from on
And
some group.
okay. So we can discuss one of these days what we want to do. Again, I prefer not to have an exam. I think it's too much to do this video conferencing exams and all that. We will discuss. Anyway, it's an elective. We have a lot of freedom. Whatever you want, I will do. And yeah, so I told last time we did the Kobe quarter theorem and we also did a corollary to that. And I said we will, now don't do the remaining parts from that chapter and we'll go to a new topic. Yeah, so why I mentioned 21st is that somehow I thought because we started late, right? Our first class was only August 10th or something. So somehow I had the impression that we will have equal number of classes as in another semester, but apparently not. So we may not do all that we wanted to do. It's okay. Anyway, this was a tough semester. So those who are interested can read and ask me questions even after the semester. So we will do infinite products today. And so really no complex analysis except in one statement. I mean, some basic things which you might know already. We will just recall. And the point is, the main word to remember in today's lecture and tomorrow next lecture is Weierstrass theorem, Weierstrass factorization theorem. So I mentioned this theorem in class 1 that if you give me a set, then I can construct a holomorphic function whose zeros are precisely elements of that set. Of course, you should assume that the set has no limit points, otherwise it's impossible. So assume that the set has no limit points and you can construct a holomorphic function whose zero set is precisely the set that you have given me. So we did such a thing for poles, right? Mittag-Leffler theorem. Now we are doing it for zeros, that is Weierstrass theorem. And we will do the theorem in the next class. Okay. So Kobe quarter theorem, what did it say? Kobe quarter theorem said that if you have a univalent function on the disk, normalize f of 0 is f prime 0, f of 0 is 0, f prime 0 is 1, then the image of the disk, unit disk, open unit disk, it contains, of course it will contain some disk by open mapping theorem, but you can say that it contains the disk centered at 0 with radius 1 by 4. And I asked you to check in this assignment that 1 by 4 is sharp. You can't better it. You can't improve that bound in general. And then we proved a corollary, and I also said that in Rudin's proof of Mergelian's theorem, this corollary plays a role. It was Rudin's remark. What was this corollary? So you had a function, not holomorphic, but it was like 1 by z plus a power series kind of term, and you assume that it's injective. And then if you take 2 points, W1 and W2, outside the image, is that correct? Does someone recall? Yeah, outside the image of
Yeah, 2 points outside image.
outside the image, then the distance, right? Mod W1 minus W2 is less than or equal to 4.
Yeah.
That's what we did. And how do I recall this? Yeah. So 2 points outside the image was used because we constructed a function which was, so take 1 point outside the image, and using that you construct a certain function which is well defined because the chosen point is outside the image. That was the starting point. And I think if I remember correctly, this function is a function for which now you can apply the Kobe-Quarter theorem. So you will get a bound, and maybe you take adjust this function by a constant function which is the other point, and when you put this together from the 1 by 4, because you have taken a reciprocal etc., mod w1 minus w2 less than or equal to 4 will come. So it's a useful corollary, though we may not see its use because we are not continuing the Mergelian's theorem and all that, but a very beautiful result anyway. So this is what we did. Today we will start this new topic. The main result, remember, this is the Weierstrass factorization theorem, which I already recalled. And an important corollary of Weierstrass factorization theorem, one should remember, even if you forget, even if you don't continue mathematics, you forget a lot of these things. Certain basic things you should always remember, which is that we know that the if you have a domain and if you take holomorphic functions on that domain, it is a ring, of course. You can add, it's holomorphic, you can multiply, it's holomorphic. It's a a ring of holomorphic functions, and because zeros are isolated as a corollary, we had noticed long back, you had already noticed in 412, your previous course, that this ring is an integral domain, right? This was long ago, maybe in our first or second class. Okay, maybe we proved it a bit later, but you had already seen it last semester. So it's an integral domain, and for an integral domain, there is this associated quotient field. So once you have an integral domain, you should naturally ask what the quotient field is, and you know the answer. The quotient field of the ring of holomorphic functions is, what is it? It is a field of
Meromorphic functions.
meromorphic functions. But the proof involves Weierstrass factorization theorem. So how do you prove this? Assume Weierstrass factorization theorem. Given any set without a limit point, you can construct a holomorphic function whose zero set is precisely that. Assume this. Then how do you prove that quotient field? So what is quotient field? It is of the form f by g, where f is holomorphic, g is holomorphic, right? So you want to say that the quotient field is precisely this, meromorphic functions. So if you have holomorphic functions f and g, then f by g is of course meromorphic. That's okay. Suppose you take a meromorphic function. You want to say that it can be written as a quotient of two holomorphic functions. So if you have a meromorphic function h, you want to say that it can be written as f by g, where f is holomorphic, g is holomorphic. So given h, you consider its set of poles. Right? You have been given a meromorphic function, you consider its set of poles. This is a set without a limit point. And to this set, you can apply the Weierstrass theorem and construct a holomorphic function whose zeros are precisely this set. Right? So if h is given, then you can construct a holomorphic function whose zero set is precisely this. Is that enough?
The order and multiplicity also we have to
Yeah,
match.
everything matching. And then what do you do?
Multiply.
Yeah, so let us say this function that you have constructed, and now if you consider h times g, because everything was matching, perfect matching, all the poles get cancelled with the zeros of g. So what is the conclusion? H times g is holomorphic, in particular meromorphic, h is meromorphic. So h times g is meromorphic, but h times g, the way you have constructed g, has no poles at all. So that means hg is holomorphic. So now you can write h as hg by g. So it is a quotient of two holomorphic functions. So it's an important corollary of my stress factorization theorem. We will do this in the next class, but let's do the preliminaries, discuss infinite products, and to prove one or two lemmas. These are easy lemmas. I could have skipped it, but I thought I will type it up. It's in Rudin and I copied from Rudin. The reason for my typing it, to be very frank, is I have taught this course a few times before, and you might have noticed that once in a while I skip some things if computations are involved, right? For example, what did we skip very recently? I skipped something, no?
The ellipse thing in the area theorem.
Yeah, yeah. I hope you looked at it. Did you look at it, Ariman?
No, I did not.
Please do. I mean, I am skipping, but you should. Yeah, so that I skipped. And maybe long back I skipped something saying that I don't want to draw pictures and yeah, what I call compact CIF. I skipped the proof. I said intuitively it's obvious, but rigorous proof can be. Yeah, so once in a while I do skip things. So the reason I put this here is that last one or two times when I taught this course I skipped all this. So I thought, okay, at least once I should do it myself. So I have put it. So you can see, I am also slightly selfish when it comes to teaching. Of course, I am teaching your class and I'm interested in your learning. But I'm also kind of, learning these things. So whatever I have done long ago, I skip now, and what I have skipped before, I am doing now. So that yeah. So these are basic things I could have skipped because complex analysis is coming only towards the very end. And these are very, easy things using triangle inequality, basic analysis. Anyway, let's do it. So you have n complex numbers and you want to talk of infinite products. So, you have done infinite series so much. So this is the multiplicative analog of all that. So an infinite product is, so infinite series, what did you do? You had partial sums and you take the limit. If the limit exists, that's what you call the series, the value of the series. So similarly here you will take partial products and you will take the limit. If the limit exists, it's infinite product. And when you analyze the summation un, one crucial point was whether un has limit 0 or not. It's not if and only if, but that was an important thing. Similarly, so what is a multiplicative analog of 0? It is 1. So whether individual terms is tending to 1 or not, etc., will play a role. So therefore, Rudin writes the individual terms as 1 plus un, and un is going to 0 or not will play a role. That's why this notation 1 plus un. Instead of writing product un, one writes 1 plus un. So this is a partial product, and when you put the modulus to this un, I have put a star. So this is exactly this partial product where there's a modulus, and that is this star. And now we have an elementary observation, right? You know that if x is a positive number, then 1 plus x is less than or equal to exponential of x. Mod un is positive, so you have this inequality. This inequality you can apply to each of these uns, and you multiply all these inequalities.
Excuse me, sir.
Yeah,
Are you using the slides or no?
I'm using slides. No, you can't see.
No, sir.
Oh, who's this?
I could see.
Uh,
Surya.
Surya, you can't see the slides.
No, sir.
So what are you seeing? Are you seeing my video?
Yes, sir.
Oh, but I have shared the screen. Now what do you see? Do you see my video throughout the screen, or do you also see, these videos? Your Surya Pratap Singh, Rahul, Vikas, Ajiman. Do you see that thing?
Yes, yes, sir.
You're seeing, no? So now let
But
me go.
not the slides.
Yeah, but now slides you can see, no?
No, sir. Maybe I can join again.
Yeah, please quit and join again. All others can see, right? Other than Ajiman, can someone else confirm? One can see the screen.
Yes, sir, I can see.
And this is Preetham.
Yes, sir.
Okay, so I assume that
Yes,
others
sir.
are able to see Surya, so you quit and join back. Hopefully the problem will be
So I
resolved.
just want to say one thing.
Yeah.
Yeah. So Surya, I think you have pinned Sir's video to this.
Possible. You might have pinched my video. So you know how to unpin, no? You might have accidentally pinned. Okay, Surya has quit. So when he comes back, maybe automatically it will be unpinned, I hope. Yeah, he has come back and now it is not pinned, maybe. Can you see Surya now? Can you
Yes,
see?
sir. Yes. Yes.
Yeah. So what happened was you have pinched my video unknowingly. That's what Preetham said. Now it's okay. Yeah, we are all learning as the course is going. So this is your third semester, no? You have one more semester to go, right? For your
Yes,
course,
sir.
and most likely that will also be online.
I think so.
We don't know for sure, but one gets that feeling. Yeah, so we
Yes.
are all learning this online thing. Okay. Anyway, not too bad. No, I'm not going that fast, right? I have cut down the pace also in last few classes. And everything is exactly from the book. So do look at the book for all the details and go through the slides and let's see. We should all manage it together. It's a difficult semester for all of you and yeah, for everybody. Okay, so you have got this inequality. You multiply all these inequalities together. What will you get on the left hand side when you multiply all these inequalities together? This is for each n. So you've got this inequality. When you multiply on the left, that's precisely Pn, right? It's product of all these 1 plus uns. No, it is Pn star. Product of all these 1 plus mod un. And on the right hand side, you will get exponential of mod u1 times exponential of mod u2, etc., which is exponential of this sum. So you've got this inequality, which we are going to use later. So it's a simple observation. And now, so these are the definitions, Pn and Pn star. Now we are going to claim that mod Pn minus 1 is less than or equal to Pn star minus 1. So this is also easy. This is induction. When n equal to 1, there is nothing to do, right? By definition, Pn minus 1 is Pn star minus 1 when n equal to 1. So assume by induction that up to n minus 1 this is true, and then you can do for n. So what you do is consider Pn minus 1. This is P subscript n minus 1 times 1 plus un, right? That is Pn. Pn is product up to 1 plus un, which is product up to 1 plus un minus 1 times 1 plus un. So this is this by definition minus 1. Okay, this much is okay, which you can write as Pn minus 1 minus 1 times 1 plus un plus un. Just multiply, you will see that this is exactly this. Okay. Now, the reason for writing like this is this you know. What do you know about the modulus of this? What do you know about that? You are assuming induction hypothesis. Therefore, the modulus of this is less than or equal to P n minus 1 star minus 1. Apply triangle inequality also. So you will get mod P n minus 1 by triangle inequality less than or equal to modulus of this times modulus of this plus modulus of this. So Pn minus 1 star minus 1, because this modulus is less than or equal to this by induction, then triangle inequality. So 1 plus mod un plus mod un, which when you multiply it out, this is induction and triangle inequality, and that is precisely Pn star minus 1, right? Pn minus 1 star times 1 plus mod un is Pn star, and the rest together is minus 1. So you have proved this inequality. All this will be used in the next result. Okay, so these are just with some complex numbers you have observed some inequalities. Okay, now you consider any set S as a sum set, not a subset of C or something, some arbitrary set S, and you consider functions un valued in complex numbers, so complex functions, and assume that these are bounded functions on some set S. So these are bounded functions, and suppose summation of the absolute value, this converges uniformly on S. Okay, and then the claim is that you can consider this product, infinite product 1 plus uns, this infinite product, and the claim is that this infinite product makes sense. It converges uniformly on S. What will be the convergence of the product? You take the partial products and the limit exists. Okay, and that limit is uniform on S. If you have this thing given to you, that summation mod uns is uniformly convergent, where uns are bounded functions, then this product converges uniformly on S. See, in Weierstrass theorem, you will be constructing holomorphic functions taking some infinite products. That's why we are analyzing infinite products. So this converges uniformly on S. And next observation, you would like to study zeros, right? I mean, Weierstrass theorem is about zeros of functions. And you want to say when this function has a zero. So the claim is f of s naught is 0, s naught is a point in S, and f of s naught is 0. What do you want? You want to take a guess? The obvious guess is correct. That's what we are going to show. When is such a product 0? What is an infinite product? These are partial
One
products.
of the UNS is -1.
Yeah, one of the UNSS -1. That's the obvious thing that you would guess, right? Because it's a product of many things. If one of them is 0, then the whole thing is 0. If and only if, hopefully, and that is true under this assumption, converges uniformly, etc. F of S naught is 0 if and only if one of the UNS naught is -1. One of this term is 0 for some n. And this is what we will prove. And moreover, the product is independent of rearrangements. You know, you could have written this product in some other way. You could have written U2 first and U1 second, and whatever rearrangement if you do. If you do any permutation of the indices and rearrange, the product is independent. So product is actually, you know, it's very good. It doesn't, it's not affected by rearrangement. So all the nice results are there. You know, when you know that something is 0, if and only if one of the terms is 0, rearrangement doesn't matter, etc. So what is the condition? This condition. Under this condition, we are proving all this. Okay. Summation of mod UNS is uniformly convergent. So let's see this. Let's take P and S, the partial product. It is up to capital N 1 plus UNS. This is the nth partial product. Then modulus of P and S is less than or equal to exponential of this. Why is this? This is exactly what we did, right? And for one complex number, I mean, for complex numbers, we did this. It's the same thing. Using that idea that 1 plus x is less than or equal to exponential of x if x is positive, and take the product, take the finite product. So this you have, and this is bounded by a constant independent of all the things involved. Why is that? That is because you know that summation mod UNS is uniformly convergent on the set S. So these are bounded functions, right? All these are bounded functions, and yeah, all these are bounded functions. Therefore, this is bounded. Therefore, boundedness is okay, and this boundedness is also uniform, independent of S and independent of N. And there you are using summation mod UNS as uniformly convergent, right? So sum is, the infinite sum is uniformly convergent. Therefore, independent of n, any of the sum is bounded. And therefore, you are getting a constant independent of the point S because of uniform convergence and uniformly bounded, therefore. And independent of this n because it's true for the infinite thing itself. So for any n, this is true. So you are getting this absolute constant. Okay. So this is because of the condition summation UNS is uniformly convergent on S. And now I would like to look at rearrangement also at the. So let n1, n2, n3, etc. be a permutation of 1, 2, 3, etc. So indices are permuted. And consider the permuted partial sum, partial product. So now you are taking, you know, instead of UK, you are taking U and K of S, and up to M, let us call it QM. So QM is for this rearrangement. Finally, we would like to say that rearrangements don't matter, and all these products are uniformly convergent and are equal. This is what we would like to show. So let this be the notation. M partial product of the rearranged product, infinite product. Now choose any epsilon positive. Later I will say that epsilon is small enough, but let's see. So there is an n notch such that this is less than epsilon. Why is this? That's because the infinite sum is
Convergence.
convergent. So the definition of that will say that given any epsilon beyond a stage, the partial sum, the difference can be made arbitrarily small, and the difference is exactly this one. So this is there, and if you choose an n bigger than n naught, choose m large enough, sufficiently large, so that the set of numbers from 1 to n is contained in n1, n2, etc. nm. This is possible, no? n1, n2, etc. is a rearrangement of natural numbers. So if you have a finite set given, I may have to choose m very, very large because it depends on how you have rearranged. But you can choose large enough, m large enough, so that in the rearrangement up to n is hit. All these numbers have come. So take such an m. So m may be much bigger than n. I don't know. It depends on rearrangement. But anyway, you can do this. And now we are going to analyze qm minus pn. What is qm? It is a partial product of the rearranged thing. 1 plus u nk of s, and pn is the original partial product. So consider qm minus pn, and we are going to write qm minus pn as pn. This is the product over these things times. So I haven't put indices because putting notations is difficult, but I will explain in words what this is. So it is pn, right? So I'm writing qm minus pn as something pn times this product minus pn times 1, which is pn. So I'm writing qm as pn times this product. So what this product is, what is this product? Pn is the original product. So those things are already there, right? 1, 2, etc. n are some ni's here. And those things you put together pn, and this unk is precisely those nks which are not 1, 2, etc. n. So the meaning is clear, no? It's obvious one. I don't know how to put the indices. So the indices are nks which are not 1, 2, etc. n. The remaining, you take pn and the remaining thing you write. Where the RHS product is over nk, which are not counted here. So in particular, these nks are bigger than n, and n is of course bigger than n naught. N naught is, depending on your epsilon, you have chosen an n naught. N is any number bigger than n naught, and the RHS, this RHS product, meaning this product, these nks are bigger than n, because anything below n has already come in Pn. So now you take the absolute value mod qm minus pn. This is, so how do you get this? Modulus of pn is modulus of pn, and why is this? This is because you're going to use one of these things that we have observed earlier. So this one, let's see. So yeah. So it is not exactly using that, it's using the same idea, right? So what you know is so you're getting e power epsilon. Epsilon is coming from here. Epsilon is coming from here. So what you are claiming is yeah. So you're going to bound
For
this.
x,
Yeah. Tell me.
for x small enough, e power x minus 1 is less than or equal to 2 times
No, I'm not
x.
talking about this one. I'm not talking about this one. Yeah, I forgot to put a pause here. I'm not here yet. I'm talking about this one. I'm talking about this inequality, and this inequality is mod Pn is here, and you know that this one will have modulus, right? This one will have modulus.
So for each un, if we put the e power,
yeah, so for this you will get 1 plus mod unk is less than epsilon exponential of mod unk, right? You will get less than exponential of mod u and k. Therefore, if you take the product of those, you will get less than exponential of summation of mod u and k. But this whole thing and all these nk's are bigger than n naught, and that is less than this sum, which is less than epsilon. So this product will have absolute value less than e power epsilon, and minus 1 is minus 1. So that explains this one. So this comes from n naught is such that this is less than epsilon. Now let's come to what so what is this explanation for this? If you choose epsilon small enough, then e power epsilon minus 1 by epsilon is less than 2. Right? You just need such an epsilon, right? Epsilon small enough so that e power epsilon minus 1 by epsilon is less than 2, then you got this inequality. So this is true for, and you had this bound, right? C was the bound. Mod PNS is bounded by C, which is independent of S and N. So mod Pn is less than C, so that is 2C epsilon. Mod Pn is less than C, and that is true for any N. C was independent of N. So this is less than or equal to 2C epsilon for small enough epsilon. Epsilon small enough is used in order to get 2 here. Okay, so this is what you have got. So the rearranged product, partial product, and the original thing, partial product, you have got an absolute bound like this. Whatever your epsilon is, I mean, not whatever, any small enough epsilon, you have got this. So now see what happens if nk is k. If you did not rearrange, what will happen? If you did not rearrange, if n1 and n1 is 1, n2 is 2, etc., then qm is pm. So qn is pn. So what you will get is pm minus pn is less than or equal to 2c epsilon, right? If you did not rearrange, the whatever argument we gave will give you that pm minus pn is less than or equal to 2c epsilon whenever m and n are bigger than something after a stage. Depending on epsilon, you choose an n naught, and beyond that you will get this. So what does that mean? That means the sequence pm is uniformly Cauchy. Right? Beyond a stage, you can make it less than 2c epsilon. And when epsilon is smaller and smaller, you can make it less than that. So this can be made arbitrarily small. So it's uniformly Cauchy, and something uniformly Cauchy, what do you know? It's uniformly convergent. And therefore, PNs converge, let us say F. So F is the product of PN. So we have proved that the original product is uniformly convergent. Okay. But now we have proved for the rearranged thing also. If you choose any m bigger than n naught, then Pm minus Pn naught is less than or equal to twice mod Pn naught epsilon. This is exactly what we have done. So I'm going to conclude about zeros, right? What was the other assertion? We wanted to say that it vanishes if and only one of the term vanishes. So if you just take m bigger than this, then Pm minus Pn naught is less than or equal to twice mod Pn naught epsilon. Apply the reverse triangle inequality here. This is less than or equal to mod Pm minus mod Pn naught, from which you will get, in particular, that mod Pm is bigger than or equal to 1 minus 2 epsilon something. This is just reverse triangle, one part of the reverse triangle inequality. And from this, you can conclude that f is the limit, f is the full product. So you have got that mod of fs is bigger than or equal to this much. Because this is the partial product. Partial product itself is bigger than this. So the full product is that correct argument? Yeah. Not because partial product is not because of one partial product, that's not correct. This is true for any m bigger than n naught. And f is nothing but the limit of pm. So there is a sequence of PMs, and each of that, the absolute value is bigger than this. Therefore, the limit is bigger than equal to this. Okay, it's a limit. F is by definition the limit of PM. So you have got this, and from this, what can you conclude? Suppose F vanishes at a point. Suppose at S naught F is 0. Then it follows that Pn naught, because these are all positive, non-negative quantities. So if this is 0, then this is 0. But if Pn naught at S naught is 0, then one of the Un is 0, because it's a finite product, and finite product, it's obvious that one is 0 if and only The product is 0 if only one of the terms is 0. So this shows that if fs is 0, then Pn naught of s is 0, which shows that one of the uns is minus 1. Other way is obvious. If one of the uns is minus 1, then one of the partial, beyond the stage, all the partial products are 0, and therefore the limit is 0. So the converse is obvious. So we have proved that part. And what about the rearrangement? For rearrangement, we have already seen that Qm minus Pn is less than or equal to 2C epsilon. And now apply triangle inequality. What do you want to show? You want to show that Qm also converges to F. So you consider mod Qm minus F. And mod Qm minus F you write as mod Qm minus Pn plus Pn minus F. And Pn minus F is arbitrarily small. Qm minus Pn is arbitrarily small. So Qm minus F is arbitrarily small. So the rearranged thing also converges to the same F. Is the proof clear? So it's a basic inequality driven proof, basic analysis proof, no complex analysis here. This is what we will use. Okay, so what we have proved is convergence of infinite product and analyzing the zero of an infinite product under one very general condition, that the summation mod uns is uniformly convergent. By the way, today also I have to stop sharp by 10:50 or something because I have another meeting. Anyway, we have time. So okay, so this part is absolutely clear, right? So under this condition, summation mod uns is uniformly convergent. You've got that this product converges uniformly, and you can analyze the zeros. This is what you would like to have. You know, the most obvious thing is true. We have rigorously proved that. Okay. So we've done this, and we are going to use this to get a complex analysis result. One more small observation. Suppose you have positive numbers, non-negative numbers strictly less than 1. And then the observation is that this infinite product is strictly positive if and only if summation un is finite. Why is that? That's obvious. You take the partial product. Infinite product is nothing but the limit of the partial product. So take the partial product and observe, because what is given is un is strictly less than 1. So 1 minus un is strictly positive. And P1 is bigger than P2. Right? Why is P1 bigger than P2? P1 is bigger than P2 because 1 minus U1, see 1 minus U1, 1 minus U2, etc. is strictly less than 1. It's strictly positive and less than or equal to 1. Less than or equal to 1. So 1 minus U2 is less than or equal to 1. Therefore 1 minus U1 times 1 minus U2 is less than or equal to 1 minus U1. P2 is less than or equal to P1. P3 is less than or equal to P2, etc. And these are all positive. So it's a monotonic decreasing sequence of positive numbers. Right? These are all positive because UNs are strictly less than 1. And therefore, it will converge. There will be a limit and a monotonic decreasing sequence bounded below. So there is a limit, and let's call the limit P. And now let's prove this one. Summation UN is finite if and only if the product is positive. So suppose summation is finite, sum is finite. We have seen already that right under this condition, we have seen that the product is 0 if and only if one of the terms is 0. Just now we saw that only this condition was required. So under this condition, the product is 0 if and only if one of the terms is 0. And this means the limit is positive. Right? Why is the limit positive?
Because all the UNs are strictly less than 1.
All the UNs are strictly less than 1, right? Because P is this product only, no? Yeah, P is that product, and we want to say that P is strictly positive. Yeah, okay, it's exactly this statement, right? I mean, 1 minus UN is 0 for some n is P equal to 0. See, P is greater than or equal to 0 because each of the Pn is greater than or equal to 0. So we want to say that P is not 0. In order to say P is strictly positive, we want to say that P is non-zero. But P is 0 is precisely one of the UNs is 1, but no UN is 1. All the UNs are strictly less than 1, so P is positive. So this is okay. Other way, if summation UN is infinity, you want to show that P is 0. So in which case P is of course less than or equal to Pn, because it's a decreasing sequence, and because each of the less than 1, and Pn is this product, and this is less than or equal to by the same thing that we have done earlier, right? 1 plus we have proved that 1 plus un is less than or equal to exponential of summation un. So this is minus un here. So exponential of minus u1 minus u2 etc. And as n goes to infinity, this tends to exponential of minus infinity, because summation un is infinity, and exponential of minus infinity is 0. And if this is 0, then p is 0. So the other way is also okay. If summation un is infinity, then p has to be 0. So that's a small observation that this is positive if and only if the summation is finite, some un is finite. And here is a small complex analysis result. This is what we will use to analyze holomorphic functions. Suppose fn's are holomorphic functions on some open set omega, need not be connected. And suppose summation n going from 1 to infinity of modulus of 1 minus fnz. This converges uniformly on compact subsets of omega. Then what the analysis that we have done, what will it say? If summation mod uns is uniformly convergent, then we know something about product 1 plus uns. So therefore, what is the corresponding product here? This is mod fnz minus 1. So 1 plus fnz minus 1, which is fnz. So this is a corresponding product. This converges only on compact subsets of omega. So we have already proved this, right? Given any set S, uniform convergence of a certain series gives uniform convergence of the corresponding product. So given any compact subset of omega, the uniform convergence of this gives uniform convergence of this on that compact subset. And therefore, for any compact subset, uniform convergence you have. And therefore, you can conclude that F is holomorphic. Why? Because what is this product? This is limit of partial product. Partial product is a finite product of holomorphic functions. Finite product of holomorphic functions is holomorphic. And then you have uniform convergence on compact subsets, and you know that if you have uniform convergence on compact subsets, then limit of holomorphic functions is holomorphic. Therefore, this F is holomorphic. Okay, so this is how we are going to construct in Weierstrass theorem holomorphic functions with prescribed zeros. We will consider infinite products suitably, and that infinite product, holomorphy is not lost. This result that we are going to use, we will be checking this aspect. Convergence of certain sums we will check, so that convergence of products giving rise to holomorphic functions is automatic. This is what we will do in Weierstrass theorem in the next class. Moreover, here you also know a zero, how many times something is a zero, the multiplicity of zeros you know. What would you like to guess? Suppose a point is a zero of this f. You know that a zero comes with finite multiplicity, right? From power series expansion we have done long back that no zero can come with infinite multiplicity. Every zero has finite multiplicity. Suppose a point z0 is the zero of this function. Can you guess a formula for its multiplicity? If everything was nice, what would be the formula for the multiplicity?
Sum of
Yeah, it will be the sum of the multiplicity of z0 for each of the fn's. And if that were the case, because this is finite, this will be an infinite sum. That infinite sum also, all but finitely many terms are 0. That also will follow. And that is true because for each z, you can take a neighborhood V in which at most finitely many fn's have a 0. Okay, so given a point z, there is a neighborhood V in which only finitely many of these fn's will have a 0. At most finitely many will have a 0. Why is that? Because otherwise, whatever neighborhood you take, if infinitely many of fn's have a 0, that should contradict this condition. This converges uniformly on compact subsets, right? Because if infinitely many fn's are 0, what does that mean? What is the meaning of this converges? That means from n0 to infinity, after a stage, this can be made arbitrarily small, right? This converges means beyond a stage, if I take n0 to infinity, then this can be made small. Given any epsilon, there is an n0, so that n0 to infinity, this is less than epsilon. But if there are infinitely many fn's which are vanishing, if there is a point on which fn vanishes, then there you have got 1 already. So you can't make that sum arbitrarily small. If one of the fn's beyond a stage, if one fn vanishes at a point, then this sum there is a contribution of 1. So it can't be made arbitrarily small. So if for every neighborhood, if there are infinitely many functions which vanishes in that neighborhood, then you cannot make this arbitrarily small uniformly. So therefore, you know that there is a neighborhood V in which at most finitely many fn's have a 0. Otherwise, on any neighborhood, this can't be made arbitrarily small, contradicting the assumption. Okay. So now what you do is at most finitely many fn's have a 0, right, on that V. So consider the product of the remaining fn's. So you have product of fn's. So some of the fn's may have a 0. Take all those together, and finitely many fn's have no 0. Consider the remaining, and that product has no 0 in V. That product has no 0 in V because each of the individual thing has no 0 in V. This is what we proved, right? An infinite product has a 0 if and only if at least one of the things has a 0. So these remaining fn's have no 0. So the product of these remaining fn's have no 0. Has no 0. And that's a holomorphic function. So this product has no 0 in V. So that's enough to prove this, because what we have proved is except for finitely many, the remaining things have no 0, have no 0. So that product has no 0. So you have written f as a finite product times a holomorphic function, and that holomorphic function has no 0. So this infinite product, this computation, you have reduced to a finite case, and for finite case, this is true that the multiplicity of a 0 is sum of the multiplicities, and therefore it is true in the infinite case. Okay, so this is preparation for the next class. That's all that we have done. So we can discuss a little bit. 10:24. We have 15 minutes. After that, I have to go. So let me stop sharing. And 19 students are here. Yeah. So all of you are coming to the class, which I am very happy about. So what? Yeah. Anyway, let's stop this recording and start the next one.